Thank you. Title. Well, I'd like to thank the organizers for inviting me. It's very nice to be here. I live up the road, but it's a little bit far to come. Anyway, I want to talk about a topic that is related to something that was said in the previous lecture. I'll try to point out when there's some common territory. But in other ways, it's a little bit far away from maybe most of the other talks in this workshop. Let me talk about the motivation. Motivation is convolution of functions. And for me, although you can do this for real algebraic groups, so I'm going to always be talking about p-adic groups, or the base field will be a non-Archimedean. I mean, for this part, okay, just for this motivational part, we have a non-Archimedean local field, and contains a sort of ring of integers, and also say a uniformizer. And let's say that the residue field, well, it's necessarily finite in order to have a non-Archimedean local field. And then we'll be considering, say, a group, which is a connected reductive algebraic group over F. But for simplicity, I'm going to say it's split. So I'm actually going to think of it as defined over O. And so for the purposes of this talk, I mean, there's a lot of abstract algebraic groups in this talk, but if you don't like that, you can always take the group to just be GLN, for example. The results are all new for these groups as well. And so when we can fix a compact, so maybe I should write this bold and then so just to make a difference between the group and its F points. So this Roman G is just the F points, and that has a natural structure of a locally compact Hausdorff group, and it has a Haar measure. There are like various choices of a Haar measure on that. And if you take J to be inside here to be a compact open subgroup, then we can consider the functions, which are the, say, complex valued, complex supported functions with values in, say, C. And that is endowed with a convolution product, which depends on our choice of measure. And it's just defined the following way. If you take two functions and you take their value at G, it's going to be the integral respect to, well, we integrate this product. Okay, so I'm changing the variable. So now we're calling the free, should have called this X, I guess. And so here, this convolution product depends on the choice of measure. For convenience, we often just declare that we've normalized it so that maybe this compact open we started with has volume 1. And then this, you think about what this is doing, this product is doing, it's actually integrating the values of F1 and F2 on pairs of elements whose product is a fixed thing, right? So the product of these two elements, G, and you're just integrating across all pairs that have that property. And this is some number that is it's a finite number because the functions have compact support. And so you can make it more explicit. Let's suppose that the Fi is the characteristic function of a double coset. So let's say these elements Wi are just for the purposes of this discussion, they're just elements of G. And such elements form a basis for this vector space. So it's enough to understand the product of those things. So if you were to multiply these things together, then it becomes just a counting problem. Okay, so it's the number of cosets of the form, say xj, which are inside the first one, and then also we work it out, the number of cosets that lie inside that intersection. And so, and that's some finite number. And in the study of Hecke algebras, one might want to understand these numbers more explicitly. And I'll give you some examples of the common ones the common structures you probably have seen before. So one natural choice of J is, say, if we take the O points of G itself. And then this is what sometimes, sometimes it's called the hyperspecial maximal compact. In this context, that's one term that's often used for this. And then inside there's often another choice, which is called the Iwahori. And this is can be defined in a number of ways, but one kind of fairly elementary way to do it is to reduce mod the uniformizer. You get, so to speak, the group over the residue field. If sometimes I'm going to just use the letter K for the residue field. And then inside there would be, say, a fixed Borel. And then the Iwahori would be just the pre-image of this. So this would be the Cartesian diagram like this. And that's another common choice, but there are others. So there are many others that are within the context of this talk. So the standard parahorics could be defined by a similar diagram. So for example, you could look at the reduction mod, the uniformizer to this, and then you could take, say, a standard parabolic subgroup, and then you can look at the pre-image. So in this case, let me just write it with a calligraphic P. So this would be what we would call a standard parabolic, standard parahoric subgroup. And that's another compact open. And that gives you a lot of them, but it doesn't give you all of them. And so once we have these various choices of compact open, the structure of the Hecke algebra is something that arises naturally in various subjects. So in the study of representations of, study of such representations is related, of the associated Hecke algebra is related to the representations of these p-adic groups, which have like Iwahori fixed vectors or parahoric fixed vectors. And I'm not going to talk about this, but this is also related to the theory of Shimura varieties, which is in some sense my main line of work. And I'm not going to mention anything more about Shimura varieties, but there's some underlying, the study of these things is sort of motivated by the study of Shimura varieties with parahoric level structure. Okay, so an example of the Hecke algebras that come up. So this particular one, it's called the Iwahori Hecke algebra. And it has a well-known presentation as a C algebra. So it would be generated by some symbols, which I'll come back to this a bit later. But there's these objects that I'm about to define in a moment, where these are the okay. Let me write it this way. So W is an element of what I'm about to define is something in the Iwahori Weil group. which is isomorphic to something very similar to what was defined in the last lecture. This is the extended affine vowel group. And such a thing has endowed on it a Bruchau order and a length function, which I'll come back to. And these symbols have the property that they satisfy a kind of braid relation. So if you take a simple affine reflection, then this kind of thing has a kind of one of two things happens. If this element is less than this in the Bruchau order, then you just get this relation. And if it's in the opposite direction, W is less than W, then you get a kind of a relation that looks like the following: Q minus 1 times TW plus Q times TWS, where Q is the order of the residue field over there. Okay. And so this is a little bit in connection to what was mentioned in the last lecture, in the sense that what you see is that this algebra here is a deformation, if Q is thought of as a variable, of the group algebra of the extended affine vowel group over C. In other words, if you specialize Q to 1, then the operation, this becomes just the usual multiplication of generators in the group algebra. But so this is like a well-known Q analog, so to speak, of the group ring on the extended affine vowel group. Okay, and what I want to tell you next is like how we define more general parahoric subgroups, because these play a role in the general discussion. So I told you how we get, so to speak, some examples of parahoric subgroups by this construction here, but this is not all of them. In the general construction, uses the theory of Bruchau-Titz-Bildung. So now I'm going to, just for simplicity, I'm going to fix a field of this. So K is any field of any characteristic. And I'm going to be considering geometric objects attached to the loop group. And so I'm going to make F my underlying field is going to be this Laurent series field. And it's going to contain the power series ring. And now my T is my uniformizer, the variable. And I'm going to again assume that G is some reductive group, but it's even going to be, again, split for simplicity, connected reductive group over O, and it's going to be endowed with the Borel and the torus. So let's say this is, we choose a torus and a Borel subgroup. Again, everything defined over O. And attached to this data, we have the Bruchau-Titz-Bildung. And also inside it, we have an apartment. A depends on the torus. I'm not going to say much about this except for it's some polysimplicial complex, which looks like a generalization of a tree, kind of a fractal object, and it carries a natural action of G of F. And this set carries a natural action of the normalizer, the F points of the normalizer. And you can draw some pictures of these apart. So this apartment is actually like a Euclidean space, which comes with a collection of hyperplanes. And so for SL3, for example, there's kind of this triangular coordinate system we'll use. And these are like this is like the choice of origin. And these walls are given by the vanishing of some of the roots. And then you have the affine roots, and you take the vanishing of those too. So if I look at all the affine roots, I would have these parallel things. And then I look at a connected component of the complement of all these hyperplanes. For example, this right here, this would be a choice of a maximal simplex, which would be, in our terminology, the base alcove. And inside this coxeter complex, there's all these different facets. So for example, this little edge here could write as a dark F for facet. That'd be an example. And so the hyperplanes are given, they're equal to the zero sets of the affine roots. So which we regard as linear functionals on this vector space. And so the Brouillard-Tits construction is the following. It says that if you fix a facet, then this is in Brouillard-Tits theory, there exists a unique connected smooth affine over O group scheme. Call it calligraphic G sub F, with the properties that its generic fiber is the original group. So in other words, I take this thing and I base change it to F. That's just identified with G. And then the second thing is that the O points, if I take this and look at its O points, that's actually equal to, well, it's connected in the sense that it's the connected fixer of this facet. So remember, the group here acts on this, and in fact, there's a subset of this group which actually acts on preserving the facet itself, fixing it as a pointwise, and that's a certain subgroup of this. And we're looking at a group scheme whose O points, well, first of all, it's connected affine smooth group scheme, but we're looking at its O points have to be in the fixer, and in fact, it's the largest group with connected fibers, which is in that fixer. Okay, so that's the characterization of the parahoric group schemes. And so attached to any parahoric group scheme, you can define various data that is related to, it allows you to construct some kind of analog of a partial affine, of a partial flag variety. So remember that if you start with G and you look at a parabolic subgroup, that gives rise to a classical, or sometimes finite, it's called finite, a partial flag variety. And now what we want to do is a kind of loop group construction of this. So in the loop group setting, I'm going to define this, but there's going to be a loop group, and there's going to be contained in it a positive loop group attached to this group scheme. And then we're going to define a quotient, which is called a partial affine flag variety. And so what are these things? So these are functors on K algebras. So which the first one takes R to E of R double parentheses T. And the second one takes to take this group scheme and plug in R double bracket T. That makes sense because this is certainly an O algebra, and so you can plug this in. And so you get this geometric object. At least a priori, it's not geometric yet. It's the way it's defined is I've given you something like that you could use to define a presheaf on this category here. So I could say take so this thing by definition is equal to the Étale sheafification of the presheaf on that category, which takes R to, well, you take the loop group bar, you mod out by the positive loop group of the parahoric. Okay, and that gives you a functor, and then you have this process of sheafifying it for the Étale topology. So that's a technical point that's not very important for the purposes of this talk. Maybe if you have seen some examples, I'll give you some examples in a moment, but it turns out that it's a fact. It's a theorem that's not trivial actually, but that this thing is represented. This sheaf is represented by an end projective end scheme over K. And in fact, the K points of it can be evaluated as the K points of this modulo K points of the thing downstairs, which in other words is G of F modulo O points of this. So all this is to say is that this object, which you can just write down as a set, is actually the K points of something that has an algebraic geometric structure.
Even if K is not algebraically closed.
Yeah, this is true for any K. In fact, this is true for any local ring, as it turns out.
What are you taking as your definition of a parahoric here?
This is a characterization of it. So there's Broad's theory tells you associated to a facet there is something called a parahoric, a connected parahoric, and I'm taking that and I'm saying that the characterization of it is it's the unique connected smooth affine group scheme over O, whose generic fiber is G, and whose O points is the fixer of F, but actually slightly subtle point here. I mean, a clean way to say this is it's the intersection of the fixer of F with the Kottwitz kernel, which is a certain homomorphism from G of F to a certain group. You just intersect that with the Kottwitz kernel, it automatically gives you the right thing. But another way to say it is just to say that it's the unique connected group scheme whose it's the unique largest connected group scheme whose O points are contained in the fixer.
And then, okay, but then for usual flag varieties, you have some kind of like subsets of the Dinkin diagram characterization of this. Do you have a subset of the affine Dinkin diagram characterization of these parahoric? Like these?
Well, the facets, okay, so the facets can be taken to be any sub. So in this, there's actually you can do any facet in the apartment, but for the purposes of up to conjugation, you might as well just assume that your facet is a something like, say, in the closure of the space alcove. And those base alcoves, of course, have their vertices are indexed by the simple affine reflections. And so it's a subset of the simple affine reflections. Yep. In fact, I was going to say a little bit about the affine vowel group and the affine. I need to tell you a little bit more about the affine vowel groups in order to do the next part. So there's another bit of overlap with the last talk. So I mentioned that there's, with attached to this data, there's an affine. And there's something called the Ewell-Horry vowel group. So the Ewell-Horry vowel group is defined the following way. You take the normalizer of the torus. So I'm just going to call it W. This is conflict with the last talk. Okay, so I'm going to call it W. I take the F points, and then I mod out by the O points of the torus. Okay, and so this sits naturally. There's an exact sequence because the F points of T of F modulo of the O points, that's the same thing as the co-character lattice. So there's a natural canonical exact sequence that looks like this. And I'll let this thing be equal to the finite vowel group. Because the finite vowel group is the normalizer of T of F mod T of F. Right? So the finite vowel group can be written this way. And so I have an exact sequence that looks like this with which has a it has a splitting that one, it has a natural splitting once I've chosen, but this depends on the choice of the O model of G. But I have a natural splitting, so I can write this also as something like the co-character lattice, semi-direct product with the finite vowel group, like in the last talk, very similar. This is something called the extended affine vowel group, because these are translations in T. These are translations coming from the co-character lattice of T, and they're not necessarily co-roots. Okay, and then, but inside here, we can look at the affine vowel group, which could be also defined as this co-root lattice, say from the terminology of last time, would be written this way. This is also the Coxeter group generated by the simple affine reflections. Okay, so it's a Coxeter group, and if in this picture right here, you look at all of the automorphisms of this thing where given by reflections through one of the walls of the base alcove, that gives you this Coxeter group, okay? Any Coxeter group has a natural structure of a length function and a Brouillard order. Yes?
So before you said not all parahorics come from reduction to the
Yeah.
finite field.
Yes.
So in terms of the subsets of thinking diagram, which ones do?
That one, for example, doesn't come from reduction mod. So this is a perfectly good facet, this piece right here.
Any subset involving the affine blue?
Yeah, you have to be a subset that's containing the origin. Because it means that you're inside G of O. Okay, so G of O is the parahoric that corresponds to the origin. And if you're going to basically be a parahoric that's inside that, you actually have to fix the origin. So that means you have to be a facet whose closure contains the origin. And any facet that does not contain whose closure does not contain the origin, that would be an example of a parahoric that does not come from reduction mod T from this guy. Now there could be a different model. In this case, every vertex is what we call special. And so there's different special model, there's different integral models that you can put here. And so for GLN or SLN or every facet is reduction mod T for some model. But there are other groups for which that's not true, like G2, for example. There are vertices that are not special. So if you give me a non-special vertex, it cannot be realized. There's no natural O model of the group that mod T gives you that parahoric, okay? But so Brouillard's theory gives you the rest. Okay, so another thing about this this structure here is that this group acts transitively on all the alcoves. Remember, the alcoves are the connected components of the complement of all the hyperplanes. The group acts transitively on them, not simply transitively. So there's a stabilizer of, say, the base alcove. And the affine vowel group acts simply transitively on all of them. So you naturally get a semi-direct product like this. Okay, this is some abelian group, finally generated abelian group, and this is this Coxeter group. And so from this, you can naturally extend the Brouillard order and the length function on this extended affine vowel group. Okay, so you get the length function and you get the thing by declaring these things to be length 0. Okay, and then the rest of the Brouillard order is determined by this. Okay, and so now then we have a basic theorem that says that, I'm going to erase this now. So the double cosets, I also need to change to loop notation. So I need to stop writing this way and start writing it just as P. So I'm going to write L of G double cosets for P. But this is now a parahoric. This is an abbreviation that I'll use for the rest of this talk. This is naturally in one-to-one correspondence with this kind of double coset, where this is this extended affine vowel group, and these things are the subgroup inside the affine vowel group that is fixing pointwise the corresponding facet. Okay, and then over here we have geometrically we have closure relations, and then here we have the Brouillard order. And it's a theorem that these two are compatible. So in other words, if you look at double cosets in here, there's a natural, you can ask when one double coset is an enclosure of the other one. Remember, this is an in-scheme, it has a natural Zariski topology. So you can talk about whether something is in the closure of another thing on this side. And it turns out it's just exactly reflected by the Brouillard order on this double coset space, which is a natural thing. I mean, there's an inherited Brouillard order on this coset space that's unique. Okay, and so then from this we can define Schubert varieties and Schubert cells. This is all just in order to even state our theorem. So we need to define Schubert. These are so-called affine Schubert cells and varieties. And so the group L, the L plus, this acts on the left on these on this affine flag variety, which is going to be this quotient. And you can look at the orbit of any point. So in particular, you could take a W in here and you look at its orbit. So YW or YP of W by definition equal to the the p orbit of W. In other words, it's equal to, you just look at, this space sitting inside, inside here. And that turns out to be, so these group schemes, these loop group schemes turn out to be in smooth. And, or sorry, project pro smooth, they're pro smooth, and they are, so these orbits are actually smooth finite dimensional varieties. This thing is a smooth finite dimensional over K variety. And then you can look at its closure with reduced structure, or alternatively, you can look at the action of P on there and look at the scheme theoretic closure of that. And either way, you get, so this thing is inside this, which by definition could be taken to be, take this closure and mod out by this. And so this thing turns out to be projective, finite dimensional, of course, K variety, which contains this thing as a dense open, but it's not always normal. So this is a strange thing. It's not always normal. There are weird examples in the affine case. So in the classical world, so all these examples are the classical flag varieties. If this P arises from a parabolic, then this finite partial flag variety is sitting inside there. So all the Schubert varieties that you've encountered from classical world, they all exist inside here. But there are many more examples, okay? And in particular, the classical ones are always normal, but in general, if in bad characteristic, these Schubert varieties are not normal. Okay, but anyway, they also have a kind of decompose, according to the Bruja order, we can write this thing as, things inside this double coset space such that V is less than or equal to W. So this is a disjoint union, not topologically. I mean, these are locally closed pieces inside here, but this tells you that the Schubert variety is the open guy plus some boundary pieces, which look like lower dimensional Schubert cells, okay? All right, so now we finally have the Schubert varieties and the Schubert cells, and now we can consider twisted products of those. So these are the so-called convolution morphisms. So what we can do is we can look at kind of take a tuple, let's call it W bullet. These are just arbitrary elements inside the Ewell-Hoare-Vowel group to the R power. And then we can attach to that a space which is written as a kind of a twisted product. And what is it? By definition, it's equal to, well, you kind of take in a way, you want to form a kind of twisted product of the closures. So you have to do something like this. Where this is like R minus 1 copies of P, but acting anti-diagonally. So in other words, if I look at this as something like this equivalence class would be the same as there's no P there. So this would be like P1 inverse G2, P2 inverse G3, and so forth until we get to the end, which is R minus 1 inverse times GRP. And so what's well defined, if you think about it, either one of these you can map to the product. G1 up to ERP. So the twisted product is set up exactly so that the product of the entries is well defined. Okay, and that product morphism is what we call the convolution morphism. And it maps to another Schubert variety, some well-determined thing here. because the image is necessarily irreducible as a scheme and reduce, well, we're giving it reduced structure and this is a surjection and it's P invariant, so it has to be a Schubert variety. Okay, and so this little thing is normally combinatorially defined using the Desmajor product, but we don't need to mention that. It can just be defined geometrically. And so this kind of object is the convolution morphism. You can see it's just the geometric analog of the integral of functions because the convolution of functions, because you're just looking at tuples whose product, if you look at a fiber, looking at the tuples whose product is just a fixed thing. Right? And we want to understand the geometry of these things. We also have a kind of what I call the locally closed or uncompactified convolution morphisms. You can take a twisted product of the cells instead of the closures. So similarly, we have a kind of twisted product of the analogous twisted product of the cells. And I call this P instead of W, instead of M. And it again maps to the, you can't control exactly that it maps to Y. It might map to some boundary pieces. So you can just talk about this kind of morphism. And so here are some well-known examples. Okay, so you probably have seen these in some way or other. So one example is the Desmajor resolution of a Schubert variety. Of course, this exists in the classical world, but also in the affine world. So the Desmajor resolutions are special cases. So what's the special case? You take each Wi to be a simple affine reflection, and you require, say, that W, their product, this is a reduced expression. If we require it to be reduced, then what happens is that this morphism MS dot from this twisted product. So, oh yeah, I should also say P is equal to B, which is now equal to the parahoric corresponding to the base alcove. So this is the Iwahori case. And so I'm looking at a twisted product of things that go like this from these Schubert cells. And it maps, in this case, it maps to just the W. Desmajor product of the SIs is W. And this is a resolution of singularities because each one of these guys turns out to be just isomorphic to P1. And this is a successive P1 fibration, so it's smooth. Yes?
It's like Schubert cell, isn't it defined over O, not
No.
it's a P order?
Yeah. It's this whole object is, this whole in scheme is defined over K. I mean, it's a K, it's a case, this is a K in scheme, and this is a part of that. This P orbit, by the way, one way you can think of it is that this is a group scheme of infinite type over K, but it factorizes through a finite type quotient. Okay, and it gives you, but yeah, it's finite dimension. This is finite type over K. It's actually finite dimensional over K. Right? Okay.
Yes. It's so the special fiber then gives you like the classical Schubert cell
No, there's no special fiber.
setting T equal to 0.
No. We're not, this is not we're not looking at this point, we're not looking at models over O. In fact, even this thing, I'm not giving this as there's no model over O unless I've extended the group. I mean, this comes up in the theory that there's ways to extend the group over a curve and look at it as a group over, say, something like O double bracket T, or where T is a different variable than the one coming into O. And then you can talk about this thing having a special fiber, but we're not doing that. At the moment, we have no models, we have no special fibers. We just are describing K schemes and K varieties. Okay, we can talk more afterward. Okay, so this is an example of a convolution morphism, this Desmajor resolution. This is a proper birational morphism. It's an isomorphism over the Y part in here. And it's smooth, and this is everything here is a smooth projective thing. So this is a classical resolution of the singularities of this Schubert variety. Okay, you can also do something I call generalized Desmajor resolution. The generalized Desmajor resolution just relaxes one condition. We don't require that the product of the SIs is reduced anymore. We just take any word. in the SIs, and just look at that. So 2 is the so-called generalized de Major resolution. And so that would be where the WIs, again, P is equal to the Iwahori. The WIs are all simple affine reflections, and the word is not necessarily reduced. And then you can again look at the same structure. You're going to have this twisted product. The thing upstairs is still smooth, but the morphism is no longer birational. So this is to something. This W star is not the product here anymore. Well, actually, it probably is, because the de Major product of these things is probably just this. Yeah, it is, in fact. So this is just the de Major product. But anyway, the point is that this is again a perfectly good convolution morphism, but it's no longer a resolution of singularities because it doesn't have to be birational. Okay. Anyway, and another example is something from the theory of the affine Grassmannian and geometric Satake. So this is another example. So in the case of the affine Grassmannian, that's a special case of a partial affine flag variety where I mod out by this kind of Iwahori. I mean, this kind of parahoric, which is a maximal parahoric. And this thing, maybe people have seen it before. Anyway, it's an in scheme, again, in projective in scheme that comes into the geometric Satake. And there's again some kind of, now in this case, the L plus G orbits of this correspond by the Cartan decomposition to just the dominant co-characters. And so I can talk about the twisted product like this. And now it naturally maps, it turns out, to the sum, the thing indexed by the sum of these co-characters. And this morphism here plays a big role in the construction of. So this is used to construct the convolution of perverse sheaves. So for example, you would take the IC complexes corresponding to these Schubert varieties, and you would just define this to be, you take the convolution morphism, you lower star it to some natural exterior products of perverse sheaves on this twisted product. And you just define this. And it turns out that this is in the category of L plus G equivariant perverse sheaves on this affine Grassmannian. And that's because this morphism here is semi-small, which is a special property that's not usually the case, almost never the case, but it's special here. It's an example of some special property. This means that the dimension of the fiber of this guy over some point, say T lambda times the base point, is less than or equal to this form. This is the formula that tells you semi-smallness holds. And that's why this thing is perverse. And this is, so the fibers and the study of this play a big role in geometric Satake. Okay, so now we have all the examples. Any questions? So now I want to just tell you the first theorem, okay? The first theorem is, it's very general. So in other words, there's no restriction on the group, there's no restriction on the field, and there's no restriction on the parahoric. The only restriction is that I've assumed my group is smooth, but I'll make, I'm sorry, is split, but I'll make a remark about that in a second. The first theorem is the following. So for all these situations, if you look at the uncompactified fibers, this is paved by products of affine lines and affine lines minus a point. And the second is that, well, this actually implies in a relatively easy way that the same thing holds for the compactified compactified fibers. All right. So what do I mean? What do I mean by paved by products? Paved by something means the following. So say a scheme X is say paved by some family of varieties C. If there exists some exhaustion by closed, the xi are closed. And the differences, in other words, the xi minus the xi minus 1 is in the family C. So a family could be, for example, a product of finitely many copies of this and finitely many copies of these. That would be like a family of varieties. And saying it has a paving simply means that you have some kind of exhaustion by closed things such that these locally closed pieces are of this form. So for example, every Schubert variety is paved by affines. It's very easy to see that, but the fibers are much more subtle. So when we look at these fibers, they're no longer stable by the action of say one of these iwahori or parahoric groups. And so it's just the geometry of them is much more complicated than the varieties themselves. Okay, and so that's the theorem. And the second theorem, the second part follows very easily from the first. So in some sense, this is the main thing. This turns out to just be like a paving by some things of this form. So you can kind of decompose this into things of this form, and though you can use the paving for this to get this result. So this is the main result. But nevertheless, I have a conjecture, which is kind of an optimistic conjecture. But I don't have any counterexample, or I don't have a proof, and I don't have a counterexample. But I can make the following conjecture. The conjecture is that that in the compactified case, these fibers are always paved by affine spaces. Not just paved by affine lines. Maybe there's some holes here, right? There's some affine lines minus a point. What I'm saying is that for these compactified ones, there shouldn't be holes. They're paved by affine spaces. Okay. So for example, this is false for the uncompactified versions. It's totally false, and you probably have already, maybe you're already aware of it because of something I wrote down on the board already, but it's false for these things here. Namely, you can just look at the case of the of B equals P and just take the W's, take W1, W2, both equal a simple reflection. So this is like when you take the convolution product for this thing here, it's like you're looking at the generators, which are these characteristic functions in the Iwahori Hecke algebra. If you square that, right, you're probably aware of this. Square this, I wrote it on the board, you get this. Right, which means the fiber here over for V equals S gives you Q minus 1 points. Right, this coefficient here is the number of points in the fiber of the convolution morphism over S. Q minus 1 cannot, I mean, the number of points being Q minus 1 means it cannot be paid by affines. It means that you necessarily have to take away a point. Right, so this is totally false for these uncompactified ones. But however, let's look at the following combinatorial thing. There's, so to speak, no combinatorial obstruction to the conjecture. Because if I, for example, if I fill in the holes on my convolution diagram, it's like I'm multiplying this by this, right? I'm filling in the holes, I add a 1 at the point, right? And then if I multiply this out, it turns out to be Q plus 1 times TS plus Q plus 1 times T sub 1. And look, these coefficients are sums of powers of Q. So there's no combinatorial reason why that the fibers couldn't be paved by affines. And it turns out this is true in general. Like you can check in general that there's no combinatorial obstruction to this being paved by affine spaces. And there are two cases where I know the conjecture is true. So one is a previous result of mine with Mark Di Cataldo and Li. So theorem 2, this is with it appeared in 2018. It's basically finished in 2016, but conjecture 2 holds. Sorry, conjecture 1. Conjecture 1 holds for the generalized Desmajor resolutions. Well, in particular for the Desmajor resolutions, but in that example 2, it holds there. And then there's another case also. So I'm just gonna, this was something like maybe around 2005, I don't know. That it holds for the affine Grassmannian if all of the mu i's are minuscule. So in particular, there's some natural family there. For any group that has minuscule co-characters, you can talk about that. This turns out to be related to the paving of some Springer fibers in the Spaltentine-Springer resolution of certain nilpotent cones for GLN. So this gives you another proof that those fibers are paved by affines. Okay,
But
but
if each WI is just simple, you can write each WI as a product of simple
Yes,
reflections that it doesn't follow from.
no,
the module.
no. And I love it if someone could figure out how to prove this conjecture in general, but no, it doesn't follow from anything like that. Yeah, so the problem is in some sense that when you look at these closures, I mean, when you look at this closure, so this thing itself has a nice moduli interpretation. It's like the set of Borels starting from some initial point up to some, it's like the family of Borels like that, right? But when you look at the closure, you no longer have this moduli, any kind of nice moduli description. So there's no corresponding thing for this. That's the problem, basically. Okay. All right, so now I want to say some applications. How am I doing? So I'm supposed to stop at what time? I'm supposed to already have stopped.
Yes.
Oh, sorry. Okay. All right. Time. Let me just say one application without saying what it really means, but one application is that this conjecture that the theorem 2 implies that that these morphisms that the BBD decomposition theorem for these morphisms here over a finite field is, so to speak, defined in the strongest possible sense over that finite field. And in particular, Frobenius semi-simple, if you take the object and you push forward, say an IC complex on this twisted product, that thing is going to be, so to speak, what both semi-simple and Frobenius semi-simple, meaning that which implies the classical results of Kazhdan and Lustig on purity and very purity of intersection cohomology of Schubert varieties, but it also implies the semi-simplicity of the category of perverse sheaves in the affine Grassmannian and various other things. So this theorem 2 is the key, one of the key ingredients in this thing, which was due to myself and Di Cataldo and Li. Okay, so I'm sorry for going over time.
Any questions for the speaker?
Yeah, so in general, what does the paving tell you at the level of cohomology?
Well, if it's paid by affines, it's very special, right? It just means that you'd have parity vanishing. The cohomology with compact support of an affine space, say L-adic cohomology of this, right? I mean, it's equal to it tells you that it's like say it's only going to be non-zero when I is 2n, so it's going to be when I is 2n, and otherwise it's 0. And so it tells you parity vanishing of the cohomology when you just have affine spaces, right? And also purity of Frobenius acting on the cohomology. So if this is something defined over a finite field, for example. So the fiber, because cohomology of compact support basically boils down, something like this boils down to giving some kind of spectral sequence where you can read off the values of Frobenius and the parity vanishing just from the fact that the individual in locally closed pieces have this cohomology properties, okay? So when you have these things here, you don't have this parity vanishing anymore, and you also don't have the purity anymore. If you have these guys, you don't have it. So there's fewer cohomological course. When you have the holes, you don't have this nice cohomological consequences. But it paid by affines is especially strong. Okay. It's very explicit, so I didn't have time, but that's one of the 4 applications. You can get a new model for like, say, weight multiplicities and like Littleman paths and things like this. So you can make it it's very explicit because the proof is very combinatorial. It's basically an induction on R. And so there's like some kind of reduction to the Iwahori case, and then there's some kind of there's a reduction step, and then there's this inductive step. And in the inductive step, you're just dealing with these simple reflections. And in the combinatorial world, that looks like alcove walks in the apartment. And so you can write down all the alcove walks that arise from this method. And it just, for example, another application I didn't time to mention is that there's these Merkovich-Valonin orbits, intersections. So this is, in the world of the geometric Satake, one studies things like this, again, viewed as varieties over the residue field. And these things inherit. So this theory that I did shows you that these results of these Merkovich-Valonin intersections also have these good pavings. Okay, so that's one thing. But also the entire theory works over Z. So that's one thing I didn't have time to go into. But there's no building for a group. If you take a group scheme over something like this, there's no building for that. Nevertheless, you can prove that all the theorems that I mentioned work for group schemes over these with suitably nice parahoric group schemes. And then when you get this result over Z, that plays a role in this sort of geometric Satake for integral motives. Okay, which I don't have time to tell you about, but that's another application, is that it gives you new proof of these things. This result for this particular thing was already known recently by Cass, Vandenhove, and Scholbach in their study of the geometric Satake for integral motives. And well, as a consequence of my paper, I just get another proof for that particular thing that they need.
Okay, so if you still have questions, you may ask, you may discuss it with the speaker individually. Okay, so our next next talk will start in 10 minutes. Okay, through started. Yeah, right. Yeah, that's.